All right, so let's talk about concrete. What is it? It's not just cement. It's a binder, which is cement and lots of other possible things like lime, fly ash, slag. We also use rocks, aggregates, sand and larger rock. It has some amount of air. It's water, of course. And then a whole bunch of other stuff that we call admixtures, which are different things that that trick the concrete into behaving the way we want it to behave. Concrete was created a long time ago. I always thought it was in Rome, but you know, I think there's an argument to be made that in Egypt and China they used lime-based mortars, and even before that, apparently these traders in Syria and Jordan used it. But it kind of fell out of favor, and the trick to making it was lost after Rome. And it wasn't until the late 1700s, 1800s that these two guys, Sweden and Aspen, kind of recreated it. And so Joseph in 1824, he created the first modern day Portland cement from chalk and clay. And shortly after that, Joseph Monnier, who made clay pots, interestingly, was interested in making pots out of concrete, but they kept breaking on him. So he added steel bars, steel hoops to prevent them from breaking. And that was the first reinforced concrete in the late 1800s. So again, the binders, back to concrete. Portland cement is the most common and most widely used and known, but we also mix in fly ash, which is a byproduct from power plants, and slag, which is a byproduct from steel manufacturing, and silica fume also is used as a cementitious product in addition to Portland. We make Portland by dumping it into these giant kilns where we apply huge amounts of heat. And by it, I mean limestone and clay. And in that process, the clay and the limestone turn into silicates, primarily these dicalcium and tricalcium silicates. And that clinker that results, I think I have a picture of it in here. Yeah, it's there on the in the middle right. That clinker is ground up, and that's what we get Portland cement out of. And so here's the most nerdy part of the whole presentation is all this chemistry, which I hate chemistry, but what you're seeing is the chemical reaction. So like the big ingredients, the big bulk of cement is these tricalcium and dicalcium silicates that make up 75% or 90% of the concrete or of the cement. You mix that with water and you get the important thing here is the COS, and this calcium silicate hydrate. That is the core structure that binds the aggregates together and really makes concrete. So this is the most important chemical part of concrete. There's a bunch of other stuff in the cement, and it's a really complicated chemical reaction that's going on. But the most important thing again are these CSH molecules. Here you kind of see what they look like. So in the early stages of concrete, you get that calcium hydroxide and this tringite, I think is how you pronounce that. But shortly after that, these calcium silicate hydrate or CSH molecules start to form. And so there's a picture of the cement grain, and then oh wait, hold on one second, I'm sorry. I've got kids that just got home from school. Yeah, so we get CSH crystals that form from the cement grains, and that's really the core of the structure of concrete. I think it's important to note, though, that concrete takes a lot of heat. I should say cement takes a lot of heat to form. So all that heat creates a lot of CO2, obviously. The chemical reaction itself also creates a lot of CO2. And pound for pound, cement is just about 1 pound of CO2 creation for every 1 pound of cement. So it's pretty carbon heavy. This is a popular image that is shared around. It kind of indicates that concrete is a relatively low embodied carbon. And that's true based on weight. But I want to point out here that it's not really true because it's a heavy material, right? So it's low carbon maybe per pound, but it's a lot of pounds. So concrete, we bind it together with Portland cement, fly ash, slag, and silica fume, like we said. And then the aggregates that we use are typically divided into 2 different types, coarse aggregate and fine aggregate. Coarse aggregate are aggregates that are retained in a 3/8 inch sieve, so anything 3/8 inch diameter and larger. And fine aggregates are really just everything that passes that sieve. Aggregates are important for a few different reasons. The durability of the concrete is in large part a function of the aggregates that are used. And then the shape and the size of the aggregates and the strength of them impact the overall strength of the concrete and its overall characteristics such as pumpability. Air is another big part of concrete. It naturally has 1 to 4% air entrapped in it. That air is kind of useless. We will add essentially a soap to concrete, which creates the little air bubbles that you see on the right, and that's what entrained air is in a concrete mix. And anytime we have freeze thaw, it's important to add this entrained air. It creates a path for the water that's naturally in concrete to expand into and prevent it from causing the concrete to crack and to basically explode on you. The last thing here is admixtures. This is like a witch's brew of different options that we can add to concrete to make it do all sorts of different things. The most common ones are like the air entrainment that I mentioned. We also do water reducing admixtures, which I'm going to talk about water and concrete in a minute. We'll use accelerators to make it set quicker, or retarders to delay the set. We might add shrinkage reducing admixtures to keep cracks at bay. We might use different like crystalline forming waterproofing admixtures in like a foundation wall to keep water from passing through the wall. Or often on like slab on grade or slab on metal deck, we might use the moisture vapor reducing admixture anytime we're gluing something down or we're worried about moisture coming out of the slab and affecting our finishes. And we might also use the nano silica. This is a more recent admixture to help with the finishing of the concrete or the durability of it. So when we specify concrete, there's a handful of things that we keep in mind. I think Helen might talk about this a bit more later, but most engineers use a performance-based specification where we leave it up to the ready mix supplier to kind of tune the mix to the project requirements. And that's more of a modern development. Historically, concrete was a prescribed mix, and I'll talk about that in the future slide. In the past, the engineer would specify exactly how much cement, exactly how much rock, everything that would go into the mix. We rarely do that anymore. But another thing we consider in our specs are the size of the aggregates. We'll use larger aggregates on foundations and areas where you have lower cover, or you want to get maybe lower cost also. We might also change when we require the strength of the concrete from 28 days, which is very common. We might use 56 or 84 days as a way to lower the cement and lower the cost of the concrete. We might also specify a maximum amount of cement if we have sustainability goals. That proportion mix that I was talking about, this is like a standard one. Historically, you might see a 1-3-3 mix, which corresponded to about a 3,000 PSI concrete. And it would be 1 part cement, 1 part stone, 1 part sand. And that mix would have been about 517 pounds of cement in it. The same mix, depending on where you are in the country today, with different admixtures and varying the rock, the size of the aggregates, etc., could be 3,000 PSI strength, but have only 250 pounds per yard, or around that. So we're making a lot of progress in concrete, thankfully. Right sizing members I think is important. And I like this quote I heard from another engineer: strength is essential, but otherwise unimportant. A lot of people are really caught up in the strength of the concrete that they deliver and provide. And honestly, as a structural engineer, I don't care a whole lot about the strength. I care a whole lot more about the durability, which in part is a function of strength, depending on what we're talking about. But I care about durability and serviceability, the life of the concrete and how will it perform over time. And so durability is a function of a lot of things. And there's a lot of things that we think about, I should say, with durability. The quality of the finishing and the curing has a huge impact on it. The exposure to freezing and thawing is very important. The aggregates that we use can be very important. We don't want to create like an alkali aggregate reaction, alkali silica reaction in concrete. And we have to consider things like sulfate attack and chemical attacks and corrosion of the rebar. There's a great guide from ACI on this, and I recommend it to all my structural engineers because the big takeaway with durability, I think, is permeability. And essentially, the lower permeable concrete, the better and more durable concrete that you're going to create. And there's a lot of ways to get to low permeability. I'm going to talk about 3 of them here, but that's the thing to keep in mind, I think, for building structures and designing concrete structures that'll last for the long haul. A few things here. So if we use a well-graded mix, so if we use, instead of just large rocks and small sand, we can pack the concrete tighter by using a well-graded mix. We can also use a lower water cement ratio. So we might want to use a water reducer, for example, to get some of the water out of there. The graph on the bottom right kind of shows the importance of that. For 4 different mixes at the same water to cement ratio, for 4 different mixes, as the water cement ratio goes down, the porosity also goes down. So water, essentially what happens is when we mix water into the mix and we have more free water than the cement is required for hydration, that water has to get out of the concrete. And in getting out of the concrete as it dries and cures, it creates the little paths that you see in that image in the top right. And those are now paths for chemicals, for water, for air to enter the concrete and cause issues in the future. So for good reason, structural engineers are worried about water. And this is why, in large part, is because it creates higher permeable concrete. So we can plug up those holes. We can use slag and fly ash to have a slower set and hold that water in longer and create less porosity. We can use crystalline waterproofing, which plugs them up. We can use these moisture vapor reducing admixtures or nano silica admixtures. And those are all ways to plug the holes and increase the durability of your concrete. So I'm coming towards the end. These are just examples of how we specify concrete at Walter P. Moore. We use a mix. We specify a different mix. We use this matrix and we specify a different mix for each application. this might not make sense for a smaller residential project, but on large commercial projects, this is how we handle it. We do a few different things here. We say when, not only what the strength of concrete is, but the strength of concrete at what time period. So you can see the bottom left, we have a lot of footings and foundations are at 56 days. That's our company standard. We have durability requirements such as the air content, and I think we've got, missing some other stuff here, but fly ash, slag. If we have sustainability goals, we might even show a maximum cement content, and then our maximum aggregate size. These are just some example mixes from Kansas City, local supplier. I can swing back by these if anyone is interested in talking about it. This is just an example. In Marin County, California, they're actually requiring that every concrete mix meet an embodied carbon limit. And I think we might see more of this in the future. And my last two slides are just comparison between a basement. This standard basement has 10 tons of carbon. If we switched it to a slab foundation, we would reduce that to 4.5 tons for the same footprint. And that's all I had, guys. So